Hi everyone, it's Alyssa. In this video, I'll be breaking down the tower generating system. My towers are made from 3 parts: walls, roofs, and spires. I have a separate module generator HDA for each part, and then the parts are assembled into towers with a third HDA. The tower generator has 2 modes. The first is manual. In this mode, the user can manually select which modules to use to assemble the tower, providing a high level of control and art directability. The second mode is blockout-based. In this mode, the user can input a blockout, and the tool will try to generate towers that match the blockout. This allows for fast iteration and large-scale generation with minimal work. Because the tool doesn't care where the blockout comes from, you could even automate the generation of the blockout with another procedural system, or use a combination of approaches. For example, in my render, I hand-dressed the towers in the foreground so I could control exactly what they looked like. But I procedurally generated the blockout for the background, so I could quickly generate many towers, HDA. I'll now dive into each tool to give an overview of how it works. The wall HDA for the towers is the same one I used for the aqueducts, so if you want more details about that one, you should go back and watch the last video. However, I did add a simple wall combining utility so I could make more interesting walls for the towers. So here I have a simple wall module, and if I just use something like this for the tower, I would get a result like this. But if I take another wall and combine it, then I get this more interesting result. I think this is a nice way for me to work more variation into the towers. The way this wall combining utility works is super simple. It takes in both walls, and it separately packs their B-boxes and the geometry itself. I see I have the preview with invisible B-box checked on, so let me check that off so we can see what's going on. Then I place the bounding boxes next to each other, like this, and then I have this option for whether or not the second module should be placed on both sides, and then I inject the original wall modules. Just like with the aqueduct generator, the reason I place the bounding boxes and then inject the walls in is so that the walls align correctly. If I didn't do that and I just plugged the walls directly in, I would get a result like this, where the walls get lined up with the edge of each other's pillars instead of the actual edges of the walls themselves. Lastly, I also take those aligned B-boxes to create a new bounding box for the combined wall module, and I merge those together. Next, let's take a look at the tower roof generator. I've put a copy and transform here so we can preview what the actual tower roof generated from this module will look like. The tower roof has 2 main parts, the base as well as the window and awnings. So let's take a look at the base first. The main settings are the number of sides, as well as shape controls like the profile and height. You can also change whether the roof is round or flat. There are also a handful of settings to control the metal framework on the roof, so how many divisions there are, and also the alternating thick bars. You can also change whether the vertical bars are parallel to each other or if they are radial. Lastly, you can clip the top of the roof to create a partial roof. This is really helpful for creating varied silhouettes in the tower generator later. The window has some simple controls to drive its shape and its scale, and the awning also has controls for how far along the roof it stretches, as well as some different controls for its shape. Now I'll dive into how the tool works. I'm pinning the parameter interface for the tool here so that we can still access it while we're inside the network. Like the wall tool, the tower roof tool is laid out roughly to correspond to the menu. So the base is generated here, the metal framework is here, and then the window and awning are here. The main shape for the roof is made by bending and resizing a line, and then revolving it. The revolve creates the round roof option, and I use the lab's edge straighten node in order to create the flat roof option. First, I create a group of edges to straighten in this wrangle, and then I feed them to the edge straighten node, which flattens them out. This geometry is the basis for the radial vertical bar shape, but for the parallel shape, I need to do a little more geometry processing. To do this, I want to dissolve the radial vertical edges and then replace them with parallel ones. Notice that I want to dissolve all of the edges that aren't the ones eligible for being straightened, except for the ones around the border. To group those edges, I use the lab's fast group unshared node to get all the edges around the border, and then I use a group combine to combine the edges I want to dissolve. After dissolving those edges, I use the lab's Polyslice node to create the vertical bars. Then I ray the geometry back onto the original roof because sometimes it loses some of its shape. Then I clip the roof, if that option is enabled. Lastly, I Boolean out the window from the roof, if there is one, and thicken the roof and window surfaces. I'll talk more about where this window shape comes from when I get to the windows. Next, let's talk about the metal roof framework. The metal framework has 3 main parts: the lattice, the sides, and the top and bottom. The top only appears in the clipped case. Let's start with the main wire framework. First, I use Lab's Fast Group Unshared node to group the border edges. Then I convert everything but those border edges into curves. In the simplest case, when alternating thickness is not enabled, a width gets set on these curves, the window gets Booleaned out, and then the curves are fed into a polywire. If the Thicken Sum Bars option is enabled, then it goes through this right chain. Here the edges get grouped by direction and then split into two chains. I create a level attribute on each point to specify which bar it belongs to. Then using that level attribute, I can group points on alternating lines to be thickened. Based on that group, I set different widths on different lines. After that, I Boolean out the window from the curves and then merge them together. Note that I have to do this Boolean while these are separate, or the width attributes will get messed up. Lastly, I use the Lab's Delete Small Parts node to delete any small unwanted pieces of geometry that might be created in the process. The process for creating the side rail is relatively simple and similar. I just group and isolate the curve that I want to add the rail to, and then sweep it with the desired geometry. Again, to create the bottom and top rails, I do the same thing, extracting the edges I want, and then sweeping the profile along them. I also have this Delete Small Parts node, because when the vertical bar shape is set to radial, I get this little extra line at the top, so without the Delete Small Parts, I end up with extra geometry, but with the Delete Small Parts, that gets cleaned up. At this point, I then group the bottom rail. Remember, if this were a clipped roof, there would be a different top rail, which is why I need to group it, and I separate it from the top rail. This gets referenced later in the network to create the roof's bounding box. You might notice this orange arrow here. This is a sticker placed with the Lab's sticker placer. I like to use these to add some visual clarification to my network when there are things that might be confusing. So, for example, if I have a chain that seems to go nowhere, I'll put down this sticker as a visual indication that the node is referenced somewhere else. The Lab Sticker Placer is a utility, not really a node, but you pull it up using the tab menu, and it pops up this window with sticker options, which are a helpful and fun way to annotate a network. You can use Ctrl-I to then edit the stickers. If you just sweep the bottom rail, the module looks fine on its own, but when it's assembled, it doesn't line up well. So let me show you what I mean. You can see that the bottom rails are going to leave gaps between each other. In order to remedy this, I create a slice of geometry with the angles that will tile correctly, and then I project the edge of the bottom rail onto that geometry. I do this by using Lab's Disk Generator and making it match the desired angle. In this case, it doesn't matter if I use the Lab's Disk Generator or the built-in Disk Generator, but I want to point out a couple features of the Lab's Disk Generator that make it pretty useful. Unlike the normal circle tool, the Lab's Disk Generator can generate its own UVs, like this. You can also cut holes out of the Lab's Disk Generator or remap its height using a ramp. But returning to the roof generator, I take the target angle disk, I align it with where the roof module will be, I extrude up the sides, and I resize it to ensure that it'll be as tall as the bottom rail. Then I isolate just one side of it. For the bottom rail, I group the points that I want to project, and I clip the rail so I only have to worry about fixing half of them, and I can just symmetrize the mesh later. Then I have two ray nodes for projecting the eligible points in both possible directions, and I symmetrize to restore the full width of the bottom rail. Then all these parts get merged together to create the roof's framework. Lastly, let's take a quick look at the roof's window and awning. The window is made pretty much the same way you saw me do it in the wall generator, where I take a line, I bend it, I scale it up and resample it, and then I use the Lab's Remove Inline Points node to reduce the number of points to only the ones essential for maintaining the window shape. Then I symmetrize the window, and I extrude it out to give myself geometry to work with for making the awning. I line the window up with the bottom rail, and then I stretch it along the roof based on the tool settings. Then I ray those points onto the roof, and I move the front out, applying the roof profile in the tool settings. You'll notice I included another sticker here, because this node uses this node as a spare input. I don't love that if I happen to have dependency links for spare inputs turned off, without this arrow it's unclear what this node does, and it looks like it might not be in use at all. To make sure this is always clear, in cases like these, I like to add a little arrow sticker, so the node doesn't get accidentally deleted. Lastly, I curve the top of the awning by turning it into lines, resampling those lines, bending each of them based on the tool settings with a vertical fall off so that the top lines get bent more and the bottom ones stay straight, and then I reskin the geometry. Then I just smooth it out and extrude it, and the surface of the window awning is done. Here is where I create the mesh that gets booleaned out of the metal framework and the roof surface. I just take the awning surface, I stretch it out to make sure it'll intersect with the necessary geometry, and then I shrink wrap it so it's manifold. Lastly, I create the rails for the awning so those can be merged together with the awning surface. The way I do this is pretty straightforward and boring, so I'm not going to go into the details, but basically I extract the curves that I want, and then I sweep them with the selected profile, which comes in here. And then I just fuse any holes that might have been created by the sweep. The only thing I want to point out here is how this system automatically makes sure not to generate these little side rails if they'd be really small. So you can see if they're longer, they get generated, but if it gets too small, they disappear. And the way I do that is just using the lab's delete small parts node. So when those lines come in and I isolate them, if they're smaller than this threshold, then this delete small parts will get rid of them so they're never swept. And that is pretty much it for the roof. The last things I want to point out are the roof bounding box, which is created here. It's pretty much just the roof surface, unextruded. The reason I do it this way is because, as you can see, if I put a bounding box around the actual geometry, when I went to try and use these bounding boxes to align the roof with other modules, it would treat the roof as bigger than it actually is because many of these points extend beyond where the roof is. So instead, I create the bounding geometry from the roof surface. If the roof's top is clipped, then I also include a bounding box of the top rail. This is so that when walls are placed on top, they don't intersect with this top rail. I deliberately exclude the bottom rail from the bounding box because I found that having the walls intersect with the bottom rail gave me better looking results. Lastly, I want to point out a couple attributes that I create on the roofs to assist in the assembly process later. The first is whether the roof is flat or round. This helps inform how the wall should be placed underneath it. The next is how many roof sides are needed to create a full roof. This informs both the placement of roof modules later as well as the walls underneath it. The last two attributes are whether or not the roof is clipped, and if it is clipped, how much it should scale the next layer in the tower by. So, for example, for this roof, it wouldn't scale the next layer in the tower that much. But if the roof looked like this, it would have to scale in the next layer by quite a lot. Most of these attributes can be taken directly from the tool's parameter interface, but the scale next by attribute has to be calculated. The scale next by attribute is calculated in this wrangle. I use the lab's extract borders node to grab only the edges of the roof to simplify the geometry. Then I delete everything but the center points. From there, this wrangle can compare the positions of the 2 points on this line to determine what the scale next by attribute should be. Then the bounding box is merged in, the attributes are applied to the geometry, and that completes the roof module generation. The last module generator we have before we get to assembling the actual towers is the spire. The spire is pretty simple, so I'm going to go through it pretty quickly. Basically, they're just two parts of the spire, the main body, where you can change the shape and the different scaling on it, as well as the ornament, which you can enable and disable, and you can also circumscribe it and add spokes. There's an option to feed in a custom model for the ornament instead of the star if you want. Diving into the spire generator, basically this bit generates the spire's body, and this bit is the ornament, where on the left is the ornament's main model, and on the right is where the spokes and the circumscribing happens. The two things I want to point out are, firstly, the spire body is created using the lab cylinder generator and then scaled and beveled. The lab cylinder generator is great for this because it can be driven using a ramp, which is referenced directly from the tool's input. The other thing I want to point out is how the spire's bounding box is made. If we just used a bound node to bound the entire spire, then the spire would always sit with its bottom right on top of the roof. However, it ends up looking kind of weird to have the spire sitting on top, but still have this bottom part curving in. So instead, I want the bounding box to start right here, so that the part that's curving in is embedded in the roof. To do this, I use the lab's split prim by normal node in order to separate what should not be included by the bounding box. Now when I use the bound node, it excludes that part of the spire. So now when it's placed on the roof, instead of looking like this, it'll be transformed down to align the bottom of the bounding box with the roof instead of the bottom of the spire, so it'll look more like this, which is much more natural. Next, let's take a look to see how all these modules come together to generate a tower. The tower generator takes 4 inputs: wall modules, roof modules, spire modules, and an optional blockout. The modules must have unique module ID attributes, so the system can tell different modules apart. I'll start by explaining how the manual mode works, because it's simpler, and then I'll show how the blockout mode builds on that system. Here's the network for the tower generator. Everything in this section is only used for the blockout mode, so we'll start by focusing on just this part of the network. First, the module inputs are read in here, with the wall modules here, the roof ones here, and the spires here. These are all processed very similarly, so I'll just walk through the roof modules for now. First, any unwanted attributes coming in are deleted so they don't interfere with the system, and then this invoke SOP runs this compile block. What this compile block does is it ensures that the module IDs begin at 0 and are consecutive. This switch is wired to the clean module IDs toggle, so if the user wants, they can disable this process. The reason for this is because although the blockout mode requires that all the module IDs begin at 0 and are consecutive, the manual mode does not. So if someone's using the manual mode and they don't want their module IDs to change from the input, they can uncheck this box. Once the IDs are cleaned, they're then fed into this subnet. In here, the module's bounding box and different materials are separated and packed individually. Packing the geometry makes the network more performant. The reason we pack the geometry separately is so that it's easier to assign different materials later. I talked about this in more detail in the aqueduct generator video, so I'll just leave it at that for this one. Once the module inputs are processed, they go into this for loop, which loops over each layer of the tower and places the modules for it. The settings for each tower layer are determined by these attribute wrangles, which set detail attributes that are read by the other nodes throughout the network. Because the whole network is compiled to make it more performant, this is done using spare inputs. However, the network gets pretty messy when I display all of them, so I like to hide the dependency links. However, it can be kind of confusing to have this chain of nodes that goes nowhere, so I use the labs sticker utility to place these stickers as a visual reminder to myself that these wrangles set the settings for the rest of the network. First, let's look at this get wall settings from roofs wrangle. If you look closely at how the towers are generated, you'll notice that the wall layers are influenced by the roof layers above them. Specifically, the number of roof slices in the roof layer above a wall layer determines how many sides are in that wall layer. So for example, this roof layer has 8 roof slices, so there are 8 wall sides in the wall layer below. Note that the number of walls per side can vary, but the number of sides will always stay the same. The wall layers are also influenced by whether the roof above them is flat or round. So this roof here is flat, so the walls are placed in a straight line, whereas this roof is round, so the walls are placed in a way that curves. The attribute wrangle iterates through the floors from top to bottom. For each wall floor, it stores whether the closest roof is flat or round and how many roof slices it has. This information is then stored in integer array detail attributes. This next wrangle just sets how many iterations the for loop should run through, depending on how many tower layers there are. For the manual mode, it just grabs this number from the parameters. Finally, this get layer settings wrangle grabs the rest of the settings from this parameter interface. These settings include what type of layer it is, so wall, roof, or spire, the module ID to be placed, the number of walls per side if it's a wall layer, the number of side setting that was set in this first wrangle, and the target radius set at the top of the tower generator settings. From there, the rest of this loop applies those settings to place the modules. So first, this loop isolates the correct module type depending on whether it's a wall layer, roof layer, or spire layer. So you can see all the modules come in and it picks the right one. Then this blast isolates the correct module ID, and this wrangle determines how much the layer should be scaled in compared to the first floor's radius. The reason we need this is because if the tower has a clipped roof like this, then the next layers need to be scaled in. If the current layer isn't a clipped roof, then this wrangle just passes the existing values along. But if it is a clipped roof, it reads the scale next by attribute off of that roof and combines that information with the scaling from the last iteration in order to update the scaling value. Next, the module is split apart from its bounding box. The rest of the placement operations will be applied to the bounding box, and then at the end, the actual module will get injected in, just like in the aqueduct generator. These nodes are responsible for placing the different copies of the wall modules, and this node is responsible for placing the copies of the roof module. There's only one of the spire module, so no copies need to be placed. This left side places wall modules that are under rounded roofs, by first offsetting the wall from the origin, and then copy and transforming it around. The correct offset from the origin is calculated here, and then fed into the transform with a spare input. Wall layers under flat roofs are placed by this right branch. The process is similar, but instead of just instancing walls around the entire layer, first, one wall side is generated, and then that side is instanced around. This current example is the same for the rounded and flat mode because there's only one wall. But if I change the settings to have multiple walls, you'll be able to see the difference. For the rounded wall, modules are just instanced all the way around. But for the flat wall, one side is created, it's realigned to the origin, it's offset, and then that side is instanced around. The roof is placed in a similar way, but it's actually simpler because no offset is needed. It's just instanced around. Then, the layer gets scaled to match the target radius. This operation is the same for wall and roof modules. I originally did this in a match size node, but I found it was faster to just do the calculations for scaling in a transform node. The spire module also gets scaled, but instead of being scaled to match the exact target radius, it's just scaled relative to the target radius, so that smaller towers will get smaller spires. Then, the module gets stacked on top of the last floor. Again, I also originally did this with a match size node, but switched it to a transform node to be a bit faster. Then, I finally replaced the bounding boxes with the actual modules. I also unpacked the bounding boxes and merged them in, so they can be used for correctly aligning future iterations. Without this step, I run into issues with aligning the modules. For example, sometimes the pillars extend slightly beyond the top of the walls, and if I align with the walls themselves rather than the previous bounding boxes, I'll end up with gaps between layers. The reason I unpack the bounding boxes is because there are attributes, like the scaling attributes, that need to be passed from one iteration to the next. However, when using the copy and transform node with pack and instance checked, these attributes don't get transferred to the pack primitives. I could attribute transfer them onto the pack primitives afterwards, but I found that it was easier to just unpack the bounding boxes, and it comes at very little performance cost because the bounding boxes are so light. Finally, after all the layers are merged together at the end, I can get rid of the bounding boxes. And that's everything for the manual method. Now let's take a look at how the blockout method works. Like I mentioned before, the blockout method takes in a set of meshes to generate towers from. These meshes must be radially symmetric, but they can have any scaling, position, or profile. I use the lab cylinder generator node in order to create my blockout towers. The lab cylinder node has an option to drive its shape with a ramp, which makes it easy to create different tower shapes. The blockout towers each need a blockout ID attribute, which is used as the random seed for each tower. This allows the tool to ensure that even if the tower is moved around, the module selection remains consistent. It also means the user can change the random seed for one tower without affecting the others. Unlike the module ID attribute, the blockout ID attribute does not need to be unique, because the system uses connectivity to differentiate between the towers, not the blockout ID attribute. Before I dive into how the blockout-based method works, I want to point out a small detail about the wall modules that I glossed over earlier. You may have noticed here that I feed in both wall modules and filler modules. The filler modules are created by the same wall generator as the wall modules, but they're shorter and intended to only be used between the walls and the roofs. So you would never see several filler modules stacked on top of each other. Within the system, these filler modules are differentiated by a wall fillers group. The system ensures that the wall modules and filler modules do not overlap by adding the maximum wall module ID +1 to each filler module. Now let's get into how the tool uses the blockout to create these towers. The actual module placement process is the exact same as the manual method. The only difference is instead of these settings wrangles determining settings based on the tower generator's multiparm, the system itself generates that information. Each of these wrangles takes care of getting the information from the right source, depending on which method is selected. Because the behavior of the rest of the nodes in this loop is determined solely by the settings from these wrangles, the system can function identically, provided these wrangles always fetch the correct settings. Now I'm going to walk through how the system generates the blockout-based information to pass to these wrangles. So essentially, these nodes just need to generate the same information that is specified by the multiparm based on the blockout. That information is the target radius, the number of floors, and each floor's type and module ID. For the wall floors, the system also needs to decide how many walls should be placed per side. Now I'm going to walk through how the system generates that information. The blockout pieces are read in here. The random seed on the tool adds an offset to the blockout ID of each tower. So this global random seed randomizes all towers, but the blockout ID of an individual tower could be changed to control the random seed on just one tower. Next, I loop through each cylinder in the blockout. I do this by using the lab's connectivity and segmentation node. This node can segment geometry based on connectivity, UV islands, proximity clustering, and custom attributes. Labs also has a helpful group named compilable segments that automatically sets up a connectivity and segmentation node along with a compile block and multi-threaded for each loop. This is intended to help users take advantage of the multi-threaded functionality of compile blocks by dividing geometry into compilable segments. This allows me to multi-thread the generation of the towers. First, I center the current blockout piece at the origin. Then, I want to determine where the floors based on this blockout will be. I use a measure node to calculate the curvature of each point. Then, I delete points based on that curvature. Next, I set some attributes on the points, including angle about the y-axis, y value, and radius, which is just the distance of a point from the y-axis. These places of high curvature indicate locations where a new floor should be created. Next, I use a fuse node, so each floor will be represented by exactly one layer of points. I use the point angle attribute I set in the wrangle above to make sure each point is only fused with corresponding points in nearby layers, rather than with other points in the same layer. Now that each floor only has one layer of points, I extract the centroid of each floor, so I have one point representing each floor. Then, I group the points that should become roofs. I do this by using the lab's split primitives by normal node to isolate the faces facing upwards. Then, I use a polyfill to turn them into closed meshes. I shift them down slightly to ensure that the points representing the corresponding floors are within the geometry, so I can add those points to a roof group. I also use a group by range node to make sure the top point is always a roof. Then, I invert the group to get the points that should be walls. And I also create a floor type attribute based on these groups to be used later. Lastly, I set the target radius for the tower based on the radius from the first floor. At this point, the system has determined the radius, the number of floors, and the type of each floor, excluding spires. Now, it just needs to pick a module ID for each floor and pick the number of walls per side for the wall floors. This information is determined almost exclusively using Vex. Although it would be possible to test and fit the modules using geometry operations in nodes instead of Vex, it would be much more expensive. Because we have all the module sizing information available to us, it's much more efficient to process this information using logic exclusively in Vex, saving the heavier geometry manipulation until the actual modules are being placed. If you're interested in seeing how you might approach similar geometry fitting in nodes, I do have an example of that in the building generator. The pillars for the buildings are placed mainly using match size and chain nodes. This is less efficient, but I left it in because I thought it could be an interesting example to have in case you want to take a look at it. Now let's take a look at how the module IDs for the roofs are selected. This wrangle picks the module IDs for the roof floors. The 0th input gets the points we've been working on. The first input gets points representing the inputted roof modules that are clipped. Each of these points' point number corresponds to the clipped roof module's module ID. It also stores that clipped roof's scale next by attribute. The second input gets the inputted roof modules that are not clipped, or full roofs. The wrangle then loops through the points representing the floors. If the point represents a roof, it then checks whether the point is the top point. If so, then it must be a full roof, so it randomly picks a full roof based on the full roof options coming in through the second input. Otherwise, the roof must be a clipped roof. The wrangle then uses the radius of the current floor as well as the target radius of the next floor in order to determine how much the clipped roof should scale the tower's radius by in order to match the blockout best. It then picks the clipped roof with the closest matching scale next by value. I later added another line of code to add a slight random offset to the target scale by value, so the clip roofs vary slightly when the random seed on the tower generator is changed. Finally, the wrangle sets the chosen module ID as a point attribute. Next, the system needs to decide the module IDs for the wall modules, as well as the number of walls per side for each wall layer. First, the system needs to update the radius attribute on each floor. In the ideal case, the target radii for each floor were perfectly matched. But because the system picks from a limited number of clipped roof modules, the true radius of each floor is likely not exactly the same as that of the blockout. So this wrangle updates the radius of each floor based on the chosen clipped roof modules and their scale next by values. Next, I set the number of sides that each wall layer will have based on the number of sides on the closest roof layer above it. With this information, I'm ready to select the wall modules. This process differs from the one used to select the roof modules in a few ways. First, the wrangle must not only choose a module ID, but must also choose the number of walls per side that should be placed. Additionally, while the points representing roofs always represent exactly one layer, in many cases, the points representing walls should actually create multiple layers of walls in order to fill up the space between themselves and the next floor. So this wrangle does not pick one wall module, but instead picks several to fill up the required space. Now I'll go into a bit more detail about how this is done. First, I get the target height of the current set of wall floors by finding the difference between the current point and the next one. You may have noticed that when the tower generator is set to blockout mode, there is a parameter for target wall width. This parameter is read in here. I then use the target radius and the number of sides to pick the number of walls per side that will most closely match the target wall width. Based on this information, I then populate an array of what the scaled height of each wall module would be if it were in this layer. I do the same thing in a separate array for the filler modules. In order to do these calculations, I need the IDs of the available wall and filler modules, as well as their bounding box dimensions. This is exactly what I feed into the first and second inputs of the wrangle. Similarly to how I had points to represent the clipped roof modules, I also create points to represent the wall inputs and the filler inputs. These points' point numbers correspond to their module IDs and have attributes storing the bounding boxes of their modules. I create these points by taking the inputted wall or filler IDs and isolating their bounding boxes. I then want to set a point attribute with bounding box size extracted from each of these bounding boxes on the representative points. However, to do this, the getBboxSize function requires a prim group. This means I need to create a group for each module containing the primitives in its bounding box. I do this by promoting the module ID attribute to a primitive attribute, and then using the lab's groupByAttribute node. This creates groups based on the specified attribute, module ID, with this group prefix. You can see the corresponding groups here in the geometry spreadsheet. So the group module_0 has the primitives with module ID 0, module_1 has the primitives with module ID 1, and so on. I could also achieve the same results using ad hoc groups in Vex. I've left that method here for anyone who prefers it, but personally, I find using the lab's groupByAttribute much more readable. I believe it's also more efficient, as under the hood, ad hoc groups need to create a new group every time the expression is run. Then I simply extract a point for each module and sort them to ensure that the module IDs correspond to their point numbers. Now back to the wall selection. After I calculate the scaled heights for each wall module and filler module, I then randomly fill the walls with modules, ensuring that I don't exceed the target height. I do this by iteratively picking random wall modules to add to the tower. If the randomly selected wall module will exceed the total height, I then remove it from the list of available modules. I repeat this process until no available walls remain. Originally, instead of using this random approach, I had a more complicated algorithm that guaranteed the optimal combination of wall modules would be chosen. I did this using a dynamic programming algorithm similar to the one used to solve the unbounded knapsack problem. However, I found that although theoretically that algorithm was more accurate, visually the difference in results wasn't noticeable. So to me, it wasn't worth the extra complexity. So I went with this random approach instead. Now I want to convert this information about the wall modules I've selected and the number of walls per side into a format that will easily be passed through the network and interpreted later. So to do this, I convert the selected walls to points with attributes for module ID and walls per side. If there is remaining space that is not filled by the selected wall modules, I then pick a filler module that will best fill the remaining space. This is why I originally called them filler modules. If a valid filler module is found, I also add a point representing that filler module, the same way I did for the walls. Now, all that's left is to take care of the spire layers. This is very simple. I just give each tower a 50% chance of having a spire. If the tower has a spire, I pick a random module ID from the inputted spires. Then I create a point to represent this spire with the same floor type and module ID attributes that the points representing the roofs and walls have. At this point, I've generated all the data that the user specifies in the manual method. These points are then fed into the settings attribute wrangles, which read the data accordingly if the blockout method is selected. Like I mentioned before, this feeds into the same loop as the manual mode to generate the final set of towers. The tool then has an option to unpack the modules so that the different materials are packed separately, just like the aqueduct generator. Lastly, it deletes any unwanted attributes or groups. Notice that the group delete references the groups to preserve parameter on the tool. This is so that the user can specify if there are any groups the tool should not delete, like the groups created by the module generators to separate the different materials for shading. I handle the shading of the towers the same way I did for the aqueducts, by generating procedural noise-based textures for the walls and roofs, and giving them random UVs and UDIMs to vary the textures. All these materials are assigned in lobs. And that concludes this video on tower generation. I hope this video was interesting, and maybe you were able to get something out of it to inspire your own setups. In the next video, we'll be taking a look at the building generation system. Thanks for watching!